Hello, I'm Carl Bradley with the University of Kentucky, and I'm going to give an overview of fungicide resistance in crops. Before we really dig in here, I'd like to just define what fungicide resistance is. So, really, the definition of fungicide resistance is when a pathogen population changes from being sensitive to a fungicide to one that is insensitive or less sensitive to a fungicide. One thing to keep in mind is that resistance may not always be complete. We call that reduced sensitivity when it's not complete. So, for instance, if a fungus has reduced sensitivity to a fungicide, that fungicide may still be effective in controlling the disease that fungus causes, but it just may require a higher dose or a higher rate of the fungicide product compared to a sensitive population. I'll just give you an example here of what this looks like in the laboratory. What you see in that picture on the right is the fungus Cercospora sogina, which causes frog eye leaf spot of soybean. This bottom row of Cercospora sogina, you can see it's growing in petri dishes here, and this bottom row is sensitive to the fungicide azoxystrobin, and this top row here is resistant to the fungicide azoxystrobin. The way you can tell is if you look at these first two plates here that are labeled control, that means that there's no fungicide that has been added to that plate. So both of these isolates are growing just fine. This next column here shows azoxystrobin at zero point 0.1 part per million added to that petri dish. And in this case, that sensitive isolate, you can just barely see some little dots there. It's just barely growing, whereas the resistant isolate is still growing pretty well. Okay. This next column shows 1 part per million. You can see that resistant isolate still growing, but you don't see any trace of that sensitive isolate. And really, it's 100 part per million is where you have to kind of get to see where you have almost complete inhibition of the resistant isolate, which looks a lot like zero point 0.1 part per million for the sensitive isolate. Okay. So that's an example of what fungicide resistance looks like when we take these isolates into the lab and do these tests. There are some different types of factors that can affect fungicide resistance, and those factors can come from two different sides. It can come from factors associated with the actual fungal pathogen, and it can come from factors associated with the actual fungicide that we're applying as well. So let's dig into what I mean about this. So when we look at the pathogen factors, one of the things that's really going to play a big role is the genetic diversity of that pathogen. The more genetic diversity there is in that pathogen population, the more likely that fungicide resistance will develop. One of the things that can promote genetic diversity in fungal pathogens is sexual reproduction. So we have some fungal pathogens that do not go through sexual reproduction. We have some that do. The ones that do, we tend to think of as being maybe a little bit higher risk for fungicide resistance happening because of that, more likely to have more genetic diversity within that pathogen population. Another thing to think about on the pathogen side is a short generation time. And what I mean by that is the time it takes from that spore to infect, cause a lesion or a spot on that leaf, and then for more spores to form within that spot. If that's a short generation time, if that only takes a couple of weeks versus a couple of months, if it only takes a couple of weeks, that means during the growing season, there's a lot more generation happening that's occurring, and you're going to have more spores out there, and the more likelihood for fungicide resistance happening in that situation. And then finally, if that fungus produces a lot of spores, that means that there's going to be more potential for those spores being a little different. Some of those maybe potentially having resistance and that fungicide selecting those out. Then over on the fungicide factor side, the site of action of the actual active ingredient is very important. If we think about a single site where that fungus is just acting at one particular site on that fungus, then it may not take very much of a change within that fungus population to overcome that, to be slightly different where that fungicide can no longer affect that fungus. So when we have a single site of action fungicide, that risk is greater for fungicide resistance compared to a multi-site fungicide, where that fungicide would be acting upon that fungus in multiple different ways in multiple different places. The fungicide application can also factor in on fungicide resistance. If we have a situation where we're applying fungicides several times during the growing season on that crop, then the likelihood for selecting out resistant isolates is going to be a lot greater versus just applying a fungicide once to a crop during the season, or maybe just using a seed treatment that would be a very small amount in just one particular place one time during the season versus a foliar fungicide application that may be applied a couple times. So the more times that fungicide is applied within the season, the more likely we're going to have fungicide resistance develop. Application history is also very important. If we think about, if you look back several seasons, have you applied the same fungicide product to that crop in the same field for the last 2 or 3 years? Versus this is the first time I've ever applied this fungicide in this particular field. So the more history there is of a particular fungicide being applied within that field, the more likely it can lead to fungicide resistance. The timing of application can also be a factor. If we think about making an application maybe preventatively, where that fungicide is in place prior to that fungus being present and trying to infect, then that's a better situation, really. Whereas if we've got a disease that's really kind of in the middle of it, and we've got a lot of spores out there already, and then we're making that application, then that type of situation could lead to a higher risk of fungicide resistance. And then kind of goes back to our first point here. What we're applying really makes a difference as well. So if we're applying just a single active ingredient product, then the risk for fungicide resistance is greater compared to applying a premix or a mixture of different products that have different modes of action. The risk is going to be a little bit lower in that situation. So how does fungicide resistance develop? One thing to keep in mind is those resistant isolates must already be in that population. The way that those isolates, those resistant isolates come to be generally is just through natural mutations that occur in fungi. One thing to keep in mind is those fungicides that we're applying, they do not cause these mutations. Those mutations occur naturally. And the rate of mutation is going to differ somewhat from fungus to fungus, but we can kind of generalize and say that these natural mutations occur in fungi at the approximate rate of 1 in 100 million. So let's just take for an example again, Cercospora sogina, which causes frog eye leaf spot of soybean, and you can see what this disease looks like here on the soybean leaf. It's got these lesions or spots that you can see here, kind of a dark border with a light colored center. And so on a susceptible soybean variety, when we have conditions that are really favorable for infection, frog eye leaf spot can be pretty severe. And I would call this picture here, the level of frog eye leaf spot in that picture, I would call that fairly severe. So this is a good example of what the situation could look like. And I didn't actually count the number of spots or lesions on this leaf, this leaflet here, but I think there's about 100 lesions. So let's just say there's about 100 lesions or spots on this leaf, okay? Now, within each of those spots or lesions, we've got approximately about 100 spores. And you can see all those spores here. This is just a close-up of the underside of one of those lesions or spots. And you can see all these little things that are spores. Let's say there's about 100 spores per lesion or spot in that picture. All right, so let's kind of think bigger. We're kind of expanding this out, doing some math here. Let's say there's approximately 30 leaflets per plant, and if you've got a 40-acre soybean field, there's about 6 million plants in that 40-acre field. We start doing the math with 100 lesions per leaflet, 100 spores per lesion, and then looking at 30 leaflets per plant, about 6 million plants in a 40-acre field. That means that we would have roughly about 1.8 trillion, with a T, trillion, spores per 40-acre field. Now let's think about that mutation rate. 1 in 100 million. If we do that math, that means that there could be 18,000 mutant isolates of this fungus in a 40-acre field. Now, those mutant isolates, they're not all going to be resistant to fungicide. Those could be mutations for lots of different things. It doesn't necessarily have to do anything with fungicide resistance. But keep in mind, some of those natural mutations that are occurring out there, one of those 18,000 could be resistance to a fungicide. So again, these fungicide-resistant isolates must already be in the population. They occur naturally. The fungicides do not cause those to exist. They occur naturally because of those mutations. And at the beginning, when we have these mutants, those resistant isolates that are out there, it's probably not noticeable at the beginning. You spray a fungicide, that fungicide is effective. You're going to have the type of control of that disease that you would expect. They're going to be a really low level of the population at the beginning. But when we make those fungicide applications, this is what we call the selection pressure. This is what selects out those individuals that are resistant. So basically what happens is we control the ones that are still sensitive, but the ones that are left are the ones that are resistant. And over time, that population of resistant isolates is going to grow. And I've got this little cartoon, if you will, that will kind of demonstrate that. So this selection pressure occurs every time a fungicide is applied. Again, here we have our leaf, our soybean leaflet that's got frog eye leaf spot. There's the close-up of the lesion, and there's the actual spores there, okay? So I've drawn these spores out here. They're obviously not to scale. They're much larger than they would normally be. But let's say that the blue ones are sensitive to the fungicide that we're going to apply. But because of this natural mutation, we've got this white one here that's actually resistant to the fungicide. And this is what's occurring naturally out in the field. We apply our selection pressure. We're applying our fungicide. Okay. What happens? Well, we take care of a pretty good amount of the blue isolates, the ones that are still sensitive, but this resistant one still remains. Okay. So let's say that it's a really bad year for frog eye leaf spot and it continues to develop, or we can even say this is the next year. We grew soybeans in that same field and we started to see frog eye leaf spot again. We make that application. What happens this time? Well, we took care of almost all the blue ones. There's just a few left, just one in this picture. The blue one again is the sensitive, but what remains are the resistant isolates. And so over time, as we make those fungicide applications, we're killing off the population that's still sensitive, but the population that remains is the one that's resistant to the fungicide. So that's why at the beginning, we don't typically see a loss of control because those resistant isolates are such a small part of that population. But over time, after we've made applications of the fungicide, we're selecting out those resistant isolates, and that's when we're going to see a failure of the fungicide to provide the type of control that we would expect. Um, so there is a committee that was developed called the Fungicide Resistance Action Committee, or FRAC. We sometimes just call this the FRAC. This was an international committee that was developed to provide fungicide resistance management guidelines. Probably one of the most important things that this committee did was to develop the FRAC group code. So this FRAC group code uses numbers and letters to distinguish fungicide groups. Fungi that are resistant to a fungicide active ingredient within a FRAC code may be resistant to all fungicide active ingredients within that FRAC code. We call that cross resistance. So let's say we've got a strobilurin fungicide, and again, we can talk about Cercospora sogina, the frog eye leaf spot pathogen. We've got a chemical called azoxystrobin, which is FRAC group 11. That fungus is resistant to azoxystrobin. Okay, so other chemicals in FRAC code 11, such as pyraclostrobin, that fungus is going to be resistant to it as well because it's in the same FRAC code, even though they're different active ingredients. You can go to the FRAC website for more information, frac.info. And just kind of a general list. This probably doesn't contain everything, but this is a pretty good coverage of the main FRAC groups that we use as foliar fungicide products in field crops. So we've got FRAC code 1, which are the methylbenzimidazole carbamates, FRAC group 3, which are the demethylation inhibitors, 7, which is a succinate dehydrogenase inhibitors or SDHIs, 11, which is the QOIs or quinone outside inhibitors. And then this is one that we don't see used very often in the crops I work with, at least, but it is labeled. This is the chloronitriles, which includes chlorothalonil. So you can see they all have different FRAC codes. And then when we look at the risk of resistance, which is the other thing that the FRAC does, is it will label these as the type of risk of resistance. And we can see with things like FRAC code 1, it's high, FRAC code 11 is high, and then we look at FRAC code 3, which is medium. Group 7 would be medium to high, and then M5 would be low. And the reason that M5 is low is the M stands for multiple site of action, whereas the others would be single sites of action. So what I want to show you here is that we do have different fungicides from different FRAC groups that we do utilize, but for a lot of these, there's still a medium to a high risk of resistance. So it is important to know what these FRAC groups look like, and it's important to be able to recognize what the products that you're using in your fields, what groups they belong to. And that's really easy information to get. All you have to do is look at the label. I've just pulled 4 different fungicide labels here. This is the front page of those labels. And I just want to point out that the FRAC codes are going to be on that front page of the labels. Look over here on the right, you can see that this product, Proline, it's a group 3 fungicide. It just contains one active ingredient. That's a group 3. Here's a mixture with Preaxor. It's a group 7 and 11. You look at Lucento up at the top left. It's a group 7 and a group 3. And then bottom left, we've got a 3-way mixture where we've got a group 3, group 7, and group 11. So knowing what those codes mean is very important. That's going to help you make decisions on the risk of resistance developing, and may help you make decisions on which products you want to use. Finally, I just want to show you that fungicide resistance is real. It is something that we are dealing with when we're trying to manage, especially foliar diseases of crops like soybean and wheat. I'm not going to go through all these, but these are just some examples, and this is probably not a complete list, but just some examples of some different soybean and wheat pathogens and the diseases they cause, and then the FRAC group codes in which those pathogens have become resistant to. In a lot of cases, we see group 11 here, which is the QOI fungicides, high risk of resistance. In some cases, we may see some that have developed resistance to more than one fret group, such as target spot of soybean. Okay, and here's a few others as well where we see multiple resistance developing to different fret groups. So keep this in mind. This is important to know that fungicide resistance is happening and it's something that we need to manage. With that, I want to thank you for your attention. If you have any questions, you're free to reach out. Thank you.